The last talk for today, and it's by Prem Kumar, and he's going to tell us about islands and Hawking radiation correlations for evaporating black holes. Take it away.
Thanks. Let me just try to get this full screen.
I think you just hit the play button, maybe. Is there a play button somewhere? No.
No.
Okay, I think I know what I need to share a different file. Sorry.
Okay.
Yeah, that works. Okay, thanks a lot to the organizers for inviting me, and of course I wish I could be there. Actually, I don't know where you would have held the conference had it been physically held, in Gandhinagar, Hyderabad, or in Bangalore, but I would have liked to visit any of those places. So this is a talk that's basically based on two papers that we wrote this year with our collaborators, Tim Hollowood at Swansea and Andrea Legramandi, who's going to be a postdoc joining Swansea this October. So he's currently a PhD student at Milano. So the broad picture is that we want to understand one of these setups that we have been discussing in the last lecture. In particular, one of these setups that involves JT gravity coupled to a bath, and where we can discuss the idea of Hawking evaporation, and we can ask questions in a dynamical or time-dependent setting. And so most of what I want to talk about will basically assume this setup and look at the consequences, the physical consequences of interesting questions that we can ask about Hawking radiation in the dynamical situation, where you have Hawking evaporation and time dependence in the setup. So what's very nice for me now is that Vijay has given a beautiful talk where he began summarizing essentially what I wanted to say, but in a very beautiful way. So all I need to do is read through the introductory slides, and hopefully everything is crystal clear already to everyone. So we know that black holes process quantum information. They're information processing machines in some sense. And quantum matter in pure state, when it collapses to form a black hole, we expect, based on unitarity, that it must eventually return to a pure state. And the reason we have this workshop, I think, is that quantum information ideas provide very powerful tools to understand how this return of information, or how this return of matter from a pure state collapsing to a black hole and its return back to a pure state, how it actually occurs. And in other words, how black holes actually process information. So again, Vijay has alluded to this classic result that we know black holes radiate like black bodies. They are hot, they have entropy, and they evaporate when they emit this radiation, Hawking radiation, and we'll denote this Hawking radiation by capital R, boldface R, at various points in the talk. Now, to paraphrase the information loss paradox of Hawking, the basic point is that given that this Hawking radiation is, by all accounts, essentially thermal radiation, if you compute the entropy in this radiation, or to be more precise, the von Neumann entropy carried by this Hawking radiation, then this entropy grows linearly with time and effectively without bound, and this is what leads to the paradox, and because this is in conflict with unitarity. Now, in some beautiful works, Page pointed out that if you actually think about the black hole Hawking radiation system as an isolated system, and we think about the von Neumann entropy of this isolated system, of course, we know that if it's in a pure state, the von Neumann entropy is 0. And if we look at the subsystem, which is the Hawking radiation, and compute its entropy or the von Neumann entropy, we should find that in general, the von Neumann entropy in the radiation increases for early times, but eventually at some point it actually turns around and then returns to 0 at late times. And so we have this identification of two time scales, the early Hawking radiation or the early times and the late time scales. And these two are essentially separated by this turnaround time, which is the Page time. And this is, of course, the curve that famously these recent papers from last year have successfully reproduced. So what is the Page time? Well, the Page time is the time taken for the black hole entropy to reduce by a factor of half, roughly. And another important point that was made by Page in his original paper, that this effect of the turnaround must be non-perturbative. So to any order in perturbation theory, if you work to any given order in perturbation theory, you will only find thermal radiation. You will not find any correlations. And so the effect that causes this turnaround has to be intrinsically non-perturbative, which is sort of in line with what we are seeing in the current developments or the recent developments. Another important point, again, making the obvious point, is that the early and late Hawking radiation are actually correlated. And this is, of course, what causes the turnaround. The late Hawking radiation is sort of the purifier, and therefore the turnaround occurs because the given late Hawking mode B is entangled with some early mode. We'll call that R sub B. So one question that we naturally have, and it's kind of one of the questions that we will try to address by doing explicit calculations, is given a late mode B, can we pin down what RB is in the early radiation? Can we pin down its purifier in the early radiation? Another question you can ask is, if you throw information into the black hole, famously as Hayden and Prescale did, if you throw a diary into a black hole, how and when can this information be recovered from the Hawking modes? So these are the kinds of questions that we want to answer. Now, important point that is also something that Vijay mentioned is that a Hawking mode B, as we mentioned here, a late Hawking mode B is entangled with an early mode R sub B. But mode B is also entangled with a partner mode which is just behind the horizon. So a partner mode A. And how can this be? Because this is conflicting with monogamy. And of course, one of the proposed resolutions was the firewall. But then the alternative resolution, which was also proposed some years ago, is that actually, in fact, the partner degrees of freedom A behind the horizon must actually be identified with RB. So in fact, the modes inside the black hole are actually contained in the Hilbert space of the early Hawking radiation. This is the A equals RB hypothesis. So the recent developments, these papers from late last year, basically have kind of provided a route to resolving these potential paradoxes. Of course, there are deep mysteries that we have already talked about and discussed, how Euclidean semi-classical gravity methods are able to actually resolve these questions, issues pertaining to unitarity. So in particular, a key element of this resolution in these recent developments is an explicit realization of this A equals RB scenario, which is that modes inside the black hole are actually contained in the Hilbert space of early Hawking radiation. So this A equals RB scenario is exactly what is realized by this new wormhole saddle point, the replica wormhole saddle points, and which are responsible for eventually turning around the von Neumann entropy of the Hawking radiation and giving us an expected page curve. So an important ingredient in what I am going to talk about is, I'm not going to talk about these replica wormhole saddles, but as was mentioned in Vijay's talks and as will probably be mentioned in other talks as well, the replica wormhole saddles and their contributions coincide with a recipe that was provided some years ago, which is that if you want to compute the entanglement entropy of some subsystem, in particular in this case the Hawking radiation emitted by a black hole, you can actually compute this the right way, or the fine-grained entanglement entropy is actually computed by a quantum extremal surface. So there is a one-to-one correspondence between the contributions of these replica wormhole saddles and the quantum extremal surfaces. So we're going to assume this relationship, or this correspondence between replica wormhole saddles and quantum extremal surfaces. What the quantum extremal surfaces do is they identify islands, regions behind the horizon in an old black hole, which are actually contained in Hawking radiation. So in other words, these islands are precisely realizing the A equals RB scenario. So another question that we could have and that we would like to answer is, what goes wrong with conventional effective field theory, or QFT, on a black hole background that actually allows A equals RB scenario to materialize? Because of course, it is highly non-trivial to state that something behind the horizon, that the degrees of freedom behind the horizon are actually contained in Hawking radiation, which was emitted way back when. So how is this consistent with locality in QFT, in particular things like how in ordinary effective field theory or curved space field theory on a black hole background, we might expect that local operators or commutators of local operators, one behind the horizon and one on the outside, which are space-like separated, should actually commute. But that, of course, it would not be consistent with this A equals RB scenario. So these are the different kinds of questions that we wanted to understand, but of course, not entirely clear that we will be able to understand all of these. But we want to understand these in a dynamical setup where we are actually thinking about black hole evaporating and therefore reducing its mass or reducing its energy. So the natural setup to consider is the setup that people have been studying and which I will review, the setup of JT gravity coupled to a CFT bath. And the CFT bath, as has been mentioned before, is something that lives in a non-gravitating region, which is a crude approximation to saying that gravity is weak in that region. Then I will talk about how we can introduce shock waves into this setup. And the shock waves cause the black hole to get excited. The excited black hole then evaporates via Hawking radiation. And then we want to understand the entanglement structure of this time-dependent evaporating black hole. What the islands look like, what the page curves look like in this evaporating black hole setup. And then we want to focus attention on looking at correlations between different modes or different subsets of Hawking radiation by computing things like mutual information. So that's the outline of the talk. So the essential physics of what we are trying to describe is captured within this effective 2D gravity plus matter system that people are talking about, JT gravity plus the CFT bath. The matter producing the Hawking radiation can be a large C CFT in 2 dimensions, which propagates in the background. The large C CFT2 does not have to be holographic. In fact, it can be just a free field theory. And the large C limit allows us to think about the matter back reaction being treated semi-classically. So matter back reacts on gravity in a semi-classical approximation. And JT gravity itself, as has been pointed out in these papers, can be viewed as a kind of S-wave sector of near horizon limit of extremal black holes in some higher dimensional theory. And so the basic content of JT gravity is given by this action. We have the usual R square root minus G term plus boundary contributions. But the non-trivial bit here is that we have a dilaton in J3 gravity, and the dilaton term, so this term in the JT gravity action, the dilaton acts like a Lagrange multiplier term, which actually enforces the condition that R equals -2. That means that the two-dimensional space-time is locally ADS2. And we want to couple this system to matter, which in this case is a CFT, large C CFT, propagating in this background. Okay, so this is all ADS2, no matter what happens, whatever dynamics happens, whatever you do to this geometry, it's always going to be ADS2. So you can always describe it or go to the Poincare patch coordinates, where it looks like the standard familiar metric for ADS. Tau here is what we call Poincare time. And I don't know what happened to this figure here, but it's come out like a badly shaped slice of bread. But what it's supposed to represent is basically that whatever we do to this background, whatever we throw into it, it always remains ADS2. The only thing that changes, or the only dynamical degree of freedom in this background, is the shape of the boundary trajectory, or the trajectory of the boundary particle. So the only dynamical degree of freedom here is the so-called boundary particle degree of freedom. So in the Poincare patch, the CFT matter, which is propagating in this background, it's in the vacuum state, which means that the stress tensor, or the expectation value of the stress tensor, is 0 in the Poincare patch. The general vacuum solutions to this JT gravity equations of motion, like I already said, they tell us that the bulk is ADS2 with some boundary, with dynamics. But the dilaton itself, this is the most general solution to the dilaton equations of motion for vacuum. So the dilaton essentially diverges near the boundary. So the boundary corresponds to phi going to infinity, and any potential singularity is, it's a reflection of any singularity that you would have had in the higher dimensional theory that corresponds to basically the dilaton going to 0 somewhere. So there's no genuine singularity in JT gravity. So if you have a non-zero temperature in the system, or if the background corresponds, you want to think of the background as corresponding to a black hole, and so there is an associated ADM mass to this, then the dilaton also has this term which is proportional to the temperature squared. So when 1 over beta squared is 0, the dilaton is 1 over x plus minus x minus, but when there's a non-zero temperature, you get this extra factor. So this is the general vacuum solution. So if you're studying the black hole, if you want to study black hole physics in this simplified setup, you think about the ADS2 or the ADS2 black hole by going to the black hole patch coordinates, where you basically do a variable change, x plus minus equals tangent hyperbolic y plus minus. And the key point here is that this is a patch within the Poincare patch of ADS2. The physical time t goes to infinity, corresponds to some finite time within Poincare patch. But you can then take the black hole patch, and think of this as a double-sided, think of it as a Kruskal extended spacetime, and you have the double-sided ADS2 black hole. And so the setup we are thinking about is this double-sided ADS2 black hole, and glued on either sides of it, we have this CFT bath, which is propagating in Minkowski space. So two-sided black hole with a Minkowski CFT2 bath glued on either side. Gravity doesn't propagate in these bath regions. And so then one asks what kinds of boundary conditions you want to put. How do you glue these two geometries together? And the natural thing to do is to put transparent boundary conditions, so that if you have radiation from this black hole, the ADS black hole, which is the thermal state, this radiation can escape out to the bath. And if the bath is held at some fixed temperature, then the radiation from the bath, which we'll talk about, is free to go into the black hole region. And so in equilibrium, the outgoing and ingoing flux are balanced. And so from the CFT perspective, where the CFT lives on all of this space-time, the incoming flux is given by the y plus component of the stress tensor at the boundary, which is at y equals 0, and that has to be equal to the outgoing flux. And because we are in a CFT in the thermal state, we know that the expectation value of the stress tensor is given precisely by pi c over 12 beta squared, which is exactly what you would get by using the usual Schwartzian transformation for the stress tensor and going from the Poincare patch or flat space vacuum to the thermal vacuum. So this is the equilibrium setup. However, if we want to discuss something more interesting where you have a non-equilibrium setup, then what really happens is that the energy balance at the boundary is disturbed. And so that means that the incoming flux and the outgoing flux are not balanced. And you can in fact see that there is an energy balance equation. The rate of change of the energy of this AdS2 black hole, or the mass of the AdS2 black hole, is given by the differential flux, the incoming minus the outgoing flux at the boundary. So when this non-equilibrium situation happens, then of course the boundary is no longer straight. The boundary particle trajectory changes, and there is actually a coordinate transformation that you need to do in order to take the geometry that you have and map it back to Poincare time. And that map, which is given by tau equals f of t, where tau is the Poincare time and t is the physical time in whatever non-equilibrium situation you're trying to describe, all the dynamics of this system is contained in this function f of t, this map that allows you to go between physical time and Poincare time. So if you know f, you know pretty much everything about the geometry that you're trying to describe or the background that you're trying to describe. Importantly, the boundary ADM energy is expressed in terms of this Schwartzian function, which also is determined completely by this map f of t. So if we know this map, we know how the mass of the black hole changes with time. We know also other things as we will go along, and I explain. So first, let's think about what happens in the equilibrium situation. So when we have the two-sided black hole, and we think about this as the thermophile double state. So the entropy of the black hole is actually given in JT gravity by just the value of the dilaton evaluated at the horizon. So the dilaton plays the role of the area. And now the recipe that we get from looking at the quantum extremal surfaces or the replica wormholes is that in order to understand the fine-grained entropy, it's not in order to compute the fine-grained entropy of any region in this geometry, it's not enough to just use the standard CFT tools, but you actually use this generalized entropy formula. What that does is it adds to the CFT contribution for the entropy of any given region, adds to it this contribution coming from the value of the dilaton at some interior point in the geometry. And then one needs to extremize this whole quantity. And when one extremizes it, one gets the true fine-grained entropy. Okay, so let's see how this works for the basic two-sided black hole or in the thermophile double state. So imagine that we have this system prepared in the thermophile double state, and we have the incoming flux at the boundary or either of these boundaries being equal to the outgoing flux. So when that happens, we have equilibrium, but we can also, in this equilibrium state, compute the entropy of the Hawking radiation in the union of these two spatial regions. So there's this capital R basically denotes this spatial slice in the CFT bath, and we want to compute the entropy of the Hawking radiation. So there are two contributions that we can think of. One is the so-called no-island contribution. This is simply the calculation of the entanglement entropy within CFT. So we use basically Calabrese-Cardy formula from way back when, it's not 2014, 2004, I think. So you just compute the entanglement entropy of this region R using the standard CFT formula and transformed to this coordinate system in the thermal state. And you will discover that that just gives you C/3 log cosine, cos hyperbolic of 2 pi t over beta. What that tells us is that at late times, that entropy grows linearly with time. And that's exactly what one expected from the initial rising part of the page curve. Now, what happens at late times is interesting because there is another contribution that you must take into account, which is the contribution coming from the island, which is by taking into account this generalized entropy formula and doing this extremization procedure. And you find that there is another contribution to this entanglement entropy, and that contribution comes from this disjoint region. And you have a region of the which we call I, the island, which is excised out, the region behind the horizon. And if you compute the entanglement entropy of this disjoint region D, which then you will find that that actually is to a very good approximation constant in time. In fact, it's just given by twice the black hole entropy. So the location of these, when you do the extremization prescription, the location of the quantum extremal surfaces is very close to the horizon. And so when you evaluate the generalized entropy at the quantum extremal surfaces, you find that the answer is pretty much given by the black hole entropy. In this case, twice the black hole entropy at temperature beta inverse, because we have the two-sided system. So what we are instructed to do is basically consider a competition between these two saddles. And so precisely what happens is that at early times you have the linear growth, and then at late times you get the contribution coming from the island, which is the dominant contribution, because that's the one that extremizes a generalized entropy. And so you have this switch over from this eternal linear growth to something that is consistent, and that's what we expect. In this case, this is what in this case, the page curve does not go down because the bath is being held at a fixed temperature. It would have gone down all the way to 0 if the bath were originally at 0 temperature. So this is the basic picture in the case of the equilibrium situation. And what we want to understand is how do we depart from equilibrium. So there are many ways of thinking about departing from equilibrium. The most natural thing to do when you have a CFT is to think about creating a local excitation in this CFT bath at some time t equals t0. Many ways to again do this. There are this so-called local excitation is what people call local quenches in the CFT bath. So a local quench can be generated in using different protocols. People have considered things like the split join quenches, and what we are going to consider is something more intuitively simple, which is inserting a local operator at time t equals 0 and disturbing the initial state of the system locally at time t equals 0 or t equals t0. So since we are disturbing the initial state, and if you think about the initial density matrix as a bra and a ket, you've got the operator O of t. You actually have two insertions of the operator because the operator perturbs both the initial bra and the ket state. And so the perturbed density matrix after this perturbation or this local quench is given by the initial density matrix at some initial temperature beta in initial inverse times O of T0 on either side. And this T0 plus I epsilon and T0 minus I epsilon is a kind of prescription that is used to regularize the total energy contained in this excitation. If you actually set I epsilon to 0, you will deposit infinite energy in this pulse that's created at times t equals t0. So the I epsilons are a nice way to regularize this energy and actually to get finite width local quenches. So that's something that we may want to think about later, but for the present purposes, we'll be thinking about a situation where epsilon strictly is taken to 0. But what happens when we insert these operators or this local quench at time t equals t0 is basically, if you compute the expectation value of the stress tensor in the CFT, all you need to do is take the OP, all you need to know is the universal formula for the stress tensor correlator with, say, two primaries. And that tells you that this expectation value describes a lump of some finite energy at time t equals t0. And then as time progresses, the lump splits into two, one a left moving lump and a right moving lump. So what we produced is basically two entangled lumps or two entangled excitations. And so we want to put these two entangled excitations, which we can approximate as delta functions. And these delta functions, one moving left, one moving to the right. And so the initial CFT stress tensor is now the initial thermal expectation value plus this delta function pulses that are moving to the left and the right. If we compute the entanglement entropy of any interval or any subsystem in the CFT, then the entanglement entropy undergoes a jump every time one of these pulses enters that particular interval, simply because these two pulses are entangled. So when one of them enters an interval or region of interest, then the entanglement entropy jumps because this guy is entangled with its purifier, which is going the other direction.
Question.
Yeah, sorry, yes.
The primary operator that you're considering has h equal to h bar. Is that right?
Yeah, in this case, yes, considering h equals h bar, but I don't think that's necessary, actually. Yeah.
Okay, and are you making any implicit assumptions about how large delta?
Yes, so that's the question. So implicitly, we're going to assume that as epsilon goes to 0, in order to keep the strength of this perturbation fixed, you want to be able to take delta to 0 as well. So strictly speaking, if I want to take the zero width limit, I also need to take delta to 0 such that delta over epsilon is fixed.
Thank you.
But that's the limit of trying to describe the zero width state.
Okay, thank you.
Okay. So the jump in the entanglement entropies and the Renyi entropies is controlled by so-called quantum dimension of the operator. It's intrinsic to the operator that we've used to prepare this initial state. So all of this was just to kind of, if you wish, a philosophical background, because at the end of the day, we're going to be thinking about these as delta function pulses. And when these pulses enter the gravitating ADS2 regions, they just look like shock waves. They are delta function sources, and that's basically the limit that we are going to be focusing on. It would be interesting to look at the finite width cases, and in fact, there are some calculations that one can actually explicitly do, but that's not something that I will discuss. So so we have these two pulses on either sides of these of the bath, or two pairs of these pulses. One is the left moving pulse. Let's focus on the right hand side bath. So we have a left moving pulse and the right moving pulse. The right moving pulse stays in the CFT bath. The left moving pulse enters the gravitating or ADS2 region. So when it enters this region, of course, the energy of the black hole state goes up. What we expect, and in fact what happens, is that the horizon moves outwards because the mass has increased, the temperature has increased. And if you actually we actually spent a little bit of time trying to understand exactly how on a Penrose diagram the boundary would bend. And indeed, you would see that the boundary bends outwards. In fact, that's the only reasonable thing it can do. So what we want to understand is exactly what is the back-reacted background in this JT gravity after the shockwave insertion. Okay, so again, before the shockwave is sent in, we have a bath which is in equilibrium with a black hole. Stress tensor expectation values in the CFT are given by the usual thermal expectation values set at some initial temperature beta in inverse. The mass of the black hole, which is the ADM mass, is given by the temperature squared of the initial state times some factors. Now at T equals T naught, we are exciting this black hole to a higher temperature, which I'll just call beta inverse. So beta in is the beta initial, beta inverse or beta inverse without an in subscript is the new excited temperature. So the energy of the black hole in the new state is going to be given by the initial energy, E beta in, plus E shock. That's conservation of energy. And that gives us a relationship between the new temperature in the excited state and the old temperature beta in. And the difference between the squares of these temperatures is given by E shock. That just follows from the previous one. So now what we have is, if you think about, again, the same system, the bath is still maintained, the CFT bath is still being maintained at the same initial temperature, beta in inverse. The black hole, the ADS black hole has gotten excited because its energy has gone up. So of course, now the balance between the two has been disturbed. So the CFT bath is at the same temperature. So the incoming stress tensor, incoming flux is again the same as it was before. Outgoing flux is different. And the difference between, and the outgoing flux is actually given simply by the Schwarzian of this function that we need to find. This is the function that will map the desired background back to the Poincare patch. So if we know what this function is, then its Schwarzian derivative with respect to t will give us the outgoing stress tensor. Our task is to find what f of t is. So now we look at the detailed balance equation, the energy flux equation, which tells us that the rate of change of energy of this black hole is basically the incoming flux minus the outgoing flux. Schwarzian pops into that equation, but the Schwarzian is again also the same as the ADM energy, as we had mentioned earlier. So you get a nice first order differential equation that tells us that E dot is to all practical purposes minus E, okay, plus some constant. And the solution to this equation is just an exponential decay in time. The important parameter in all of this is this parameter K. This is a very important parameter. This K effectively controls the coupling between the CFT bath degrees of freedom and the gravity degrees of freedom. There's another way we can think about this, because this is ADS2 coupled to a CFT2. The ADS2 could also be thought of as a CFT1 or a quantum mechanical system which resides on an impurity which is at the boundary of a CFT2. So we can think of this in different ways. We can think about this whole setup holographically, where the ADS2 is replaced by a quantum mechanics, and the quantum mechanics describes some boundary degrees of freedom of the CFT2. And this parameter K basically describes the coupling of the CFT2 bath to the quantum mechanical degrees of freedom. Now, this coupling will be taken to be weak, and it has to be small in order for the semi-classical description to apply. And we are, after all, doing semi-classical physics here because we are feeding in the expectation value of the stress tensor into the gravity equations. That's a semi-classical approximation. Okay, so the semi-classical approximation requires that K be much smaller than 1, and that is something that is implicit in all of this. Now, solving for this energy flux equation, like I said, just tells us that the energy decays exponentially in time. Very simple. But it also tells us that we can write this energy in terms of an effective temperature squared. What is this effective temperature squared? It's precisely what the old temperature was, plus a nice time-dependent factor. And so, in fact, if you take this seriously, it's telling you that the excited black hole temperature decays exponentially back towards the original temperature. So we started with some initial temperature, excited it, and then the system is relaxing back exponentially, and at late time, system will go back to the initial thermal state with the initial temperature. But this relaxation occurs slowly because the coupling K, which sets the evaporation timescale, the Hawking evaporation timescale, this coupling is small, and therefore the timescale is 1 over K, which is much bigger than 1 in appropriate units. So this is the post-shock wave. Now, we're still not done with discovering what the background itself is. To solve the background, you need to solve the Schwarzian equation. So the energy, the ADM energy, is given by this Schwarzian derivative of f of t. We now know exactly what the ADM energy is because that's written in terms of this exponential function. So you just need to solve this third order differential equation to find what f of t is. The solution to the Schwarzian differential equation is only determined up to SL2R Mobius transformations. But then these Mobius transformations, these A, B, C, and D, can be fixed by matching on to the equilibrium state at time t equals t0. So everything can be determined. Very nicely in the system, everything can be solved in terms of Bessel functions. So that's nice to know, ratios of Bessel functions. But Bessel functions are unwieldy, so we will be doing some approximations because it's not just enough to find what this background is. We also want to be able to compute things like entropy. And the entropy requires us to do this extremization trick, and extremization is going to be very difficult if you're going to be dealing with things that have ratios of Bessel functions. We might end up having to do things numerically. That's not what we want to do. So an interesting thing about this entire scenario and with this shock wave, with this shockwave setup, which then triggers evaporation, is that the dilaton can be solved for exactly in terms of the same function f that we have determined. So if one looks at the dilaton equations of motion, it's actually not obvious that you can solve it in a simple way, because it looks like you have to invert differential operator, and it looks like you have to deal with memory functions and Green's functions that are non-local. But it turns out that in this specific situation with the kinds of stress tensor components which are non-zero, the dilaton can be solved for exactly in terms of f. So if we have a nice way to approximate f, we can study this entire system analytically in some approximation. So this is the approximation that we're going to look at. So I'm going to describe two broad approximation schemes. Both are slow evaporation approximations. So both involve assuming that k is much smaller than 1. This coupling constant k is much smaller than 1. But then we will also narrow it down a little bit further. So the first approximation is where we think about the initial state, which is a high temperature black hole, and we take the initial temperature to be very large. So in terms of the inverse temperatures, we are saying that beta in is much, much smaller than k inverse. So this is the, which is like saying that k times beta in is much, much less than 1. So that is still a slow evaporation approximation, but it's very specific. We are thinking about k beta being very, very small. So in this limit, it's very nice that these Bessel functions actually simplify very nicely. There is an integral representation of Bessel's functions, which you can then evaluate using a saddle point method, and then you find a very simple result coming out. That in fact, the complicated looking Bessel function solution in this limit can be represented by things that look pretty much thermal. If you recall, I talked about the black hole patch in equilibrium, and there was a coordinate transformation which involved a tangent hyperbolic function. Not surprising, because we are talking about thermal things, and so we should get periodicity in imaginary time. In the non-equilibrium situation, all that's happening is that the temperature inside the tangent hyperbolic is being replaced by this quasi-thermal time-dependent temperature. So if beta effective was constant, we would get back the old formula, but beta effective being a function of time, the integral appears inside it. So it's like a quasi-thermal relaxation. There's another regime that we will consider, which is the regime where the initial state is actually at 0 temperature. So the initial state this is more akin to what black hole formation and evaporation should be like, because the initial state is extremal, 0 temperature. We throw in a shock wave, we excite the black hole, we excite the system and form a black hole, and then the excited black hole evaporates back down to 0 temperature or to extremality. So the second scenario is where beta inverse initial is exactly 0, and there we consider a slow evaporation limit, k much smaller than 1, with kt fixed, which means that we look at all time scales, arbitrarily small time scales, but up to time scales of order 1 over k. So we want to focus attention on time scales of the order of 1 over k in the second approximation. And so in that approximation, what we find again, that this function f of t, which is like the key function, which is underlying everything, again we get this tangent hyperbolic with an argument which has this very simple exponential dependence on time. So important between these two scenarios is that the first scenario is actually valid for the first approximation, high temperature approximation, valid for all times, but in the high temperature limit, high temperature slow evaporation limit. Second scenario is the slow evaporation scenario, valid for time scales of order 1 over k, which are long time scales, but not arbitrarily long. In particular, we know that this approximation will break down for times of order k inverse log k. Okay, so we have some quasi-analytic expressions. What do we want to do with them? Well, we want to compute entropies. We want to compute entanglement entropies. So we already know that the black hole entropy is given by the value of the dilaton at the horizon. So entropy as a function of, now we basically take phi, the solution for the dilaton that we described in a couple of slides before, and treat it as a function of time. And so this entropy is going to be a function of time. And in fact, we find that the black hole entropy is given by a very simple formula involving this function f hat, which is related to f by an Mobius transformation. Not very important, but in this slow evaporation regime, the high temperature slow evaporation regime, where the initial black hole state, initial state is the thermal state at high temperature, we find that the black hole entropy is given by the usual formula for the black hole entropy, except that now the temperature is this effective time-dependent temperature. So that's very simple. We can now compute things like the entropy in the Hawking radiation. So we are now excited, we have excited the high temperature initial black hole by putting in shock waves. It's gone on to a higher temperature. And now what's happened is that the horizon has now moved out, displaced, and now we want to compute the entropy of all the Hawking radiation that's received by the spatial region, the bath region of the CFT. So that has two contributions. So one is the Snow Island contribution, where all you're doing is basically saying, well, this entire state is in a pure state, in the thermophile double state initially. So if I want to compute the entanglement entropy of R, then it's basically equal to the entanglement entropy of D. The entanglement entropy of D is given by usual Cardy-Calabresi formula. Sigma 1, 2 is like the invariant length square between these two, between points 1 and 2. Omega 1 and omega 2 are conformal factors that you have to throw in because the spacetime is not the spacetime has a non-trivial conformal factor associated to ADS2. So those factors are thrown in, but this is the usual CFT result. On top of that, you have twice the contribution from the intrinsic entropies of the shock waves themselves. These are basically controlled by the quantum dimension of these operators that we use to produce these local quenches. So you compute this no island entropy. So this is the standard box standard CFT calculation for the entanglement entropy. And what you will find is that in this time evolving geometry, the entanglement entropy of S of R, the no island contribution, looks piecewise linear. So at early times, it increases linearly with some slope, which is determined by the initial temperature. At times of order 1 over k, which is kind of intermediate but long time scales, the slope increases. That's because you've pumped energy into the system. So this the no island entropy grows faster. And then at very late times, because the system is going to relax back to its initial temperature, the linear growth comes back, but it now reverts back to the old slope. So you've got this piecewise linear growth so instead of a linear growth with the same slope, you have a piecewise linear growth. Now, there is something interesting that happens because, in fact, you can look at island contributions, the quantum extremal surfaces, and there are two kinds of situations that can happen. One where the quantum extremal surface is in front of the shock wave, which means these blobs that you see here, these are the locations of the putative quantum surfaces, quantum extremal surfaces. They avoid the shock wave. In other words, they occur. They are in front. They are before the shock wave. The shock wave hasn't got to them, and so there are saddle points that you get by extremizing the generalized entropy formula. So you evaluate the dilaton in this time evolving background at some location at a putative location of this quantum extremal surface. Add to it the CFT contribution to the entropy, then extremize the whole thing, and then find the location of this quantum extremal surface. So you can do the whole process analytically, and you discover that there is this island contribution with the quantum extremal surface in front of the shock wave, and the way it behaves again is piecewise linear. At early times, it's a constant. In fact, its value is given precisely by twice the entropy of the initial black hole state plus twice the entropy of the intrinsic entropy of the shocks, and that's because the initial state of the black hole has its own initial entropy. We've thrown shocks into it, and those that's reflected in the initial flat behavior of this entropy contribution from the quantum extremal surface. Then at slightly later times, this shows linear growth with a slope which is again dictated by the temperature of the initial state. That slope changes, becomes faster, and then reverts back to linear growth at late times. So we now have got another potential contribution to the entanglement entropy of Hawking radiation, which is not just the pure CFT result, but it's an island contribution, but it also has piecewise linear bits to it. And then we have a third contribution, which is when the quantum extremal surface resides behind the shock wave. So the shock wave is already passed, and this quantum extremal surface is found by doing the same procedure, but in this new excited black hole state, and you discover that the quantum extremal surface, very interestingly, in this excited state just after the shock wave has excited the system, the quantum extremal surface actually lies behind the horizon. This is actually interesting because in all equilibrium situations, the quantum extremal surface always lies close to the horizon, but slightly outside. But in a non-equilibrium situation, just after exciting, the quantum extremal surface actually, after the shock wave, lies just behind the horizon. And in fact, the entropy is given approximately by the entropy of the excited black hole state. So it's time dependent, and it interpolates between the excited black hole entropy and eventually relaxes back to the original black hole entropy at late times. Interestingly, the quantum extremal surface migrates from behind the horizon at early times after the shock wave has passed, and then comes out of the horizon at late times. So somehow, for equilibrium situations, the quantum extremal surface always seems to lie behind the horizon. So this is kind of a picture that summarizes the positions of these different quantum extremal surfaces. And I've just sketched them here, but I've already told you in words what they represent. We at early times, we have the quantum extremal surface, which basically tracks the quantum extremal surface of the equilibrium situation. Then it departs from that, and it starts dominating over the usual CFT result, but it also has linear growth in time. And at late times, it can be overtaken by the quantum extremal surface that pops out behind the shock wave. And so we get different kinds of scenarios that we have multiple saddles in the system and multiple kinds of scenarios that can happen. And there are different dials that you can actually turn. So different dials include the insertion time for the shock wave T0 relative to the original page time, the magnitude of the shock, the energy of the shock wave, and the entropy of the shock wave. So all of these dials can be dialed, and you can get different kinds of transitions or different kinds of saddles dominating. And so these are kinds of the scenarios that I've sketched here. One where the no island contribution to the entropy starts off at early times, and then after the shock wave has been inserted, you still have the no island contribution, but then at late times it's overtaken by this quantum extremal surface contribution from behind the shock wave. But you can have another situation where you have the transition between the no island contribution and the island contribution to the entropy at early times before the shock wave has been inserted. And then you get a transition between the two kinds of quantum extremal surfaces, the one which is behind the shock wave, and the one which is in front of the shock wave. And so there's various kinds of phase transitions that can occur, and different kinds of rearrangement of the entanglement structure of the black hole that's excited. Okay, so now I want to kind of switch gears and move to the case which is kind of interesting, where we can do more. We can ask more interesting questions. In particular, we can ask questions about the correlation between different Hawking modes. So this is the situation where we start. This was the second scenario I outlined, where the initial black hole state is at 0 temperature. So we have the extremal state. And so in the extremal state, beta inverse is 0. The black hole is actually one-sided. And the extremal black hole, it turns out, is already at an island saddle. There is no island contribution to the entanglement entropy or the von Neumann entropy of the radiation. And now you insert the shock wave, and you find that once you insert the shock wave, there are two kinds of quantum extremal surfaces. One where you have the quantum extremal surface in front of the shock wave, and another where you have quantum extremal surface behind. Both of them have a nice but simple exponential dependence on time. So these are the contributions to the entropy of the Hawking radiation. emitted by the excited black hole, excited state. And we are working in the regime where K is small, so we are in the slow evaporation limit, but KT is fixed. So in this, all we are interested in is basically the crossover between these two. So we have, at early times, the entanglement entropy in the von Neumann entropy of the radiation is dominated by the quantum extremal surface in front. At late times, it's dominated by QS, the quantum extremal surface behind the shock wave. And the crossover point is precisely what we would call the page time. So here we find that the page time for this evaporating black hole, so we have the extremal state with a shock wave inserted, now evaporating, has a page time which is given by 2 over k log 3/2. Very nice result, but it tells us that the page time is set by 1 over k. And so this is well within the regime of the slow evaporation approximation that we've been using. Now we can use this setup to actually look at more fine-grained information. We can look at multiple intervals. So I've been talking about so far about Hawking radiation, about the von Neumann entropy of all the Hawking radiation that is emitted and received by the bath. But we can actually look at correlations of the Hawking radiation by dividing up the bath region into subsets. And we can examine this correlation by looking at a less crude tool, which is the mutual information. And so we can think about computing the entanglement entropies of multiple intervals. So this is something that we did in the paper, and it's kind of technical, but so I didn't want to give the formula, but you can actually write down the CFT result for multiple disjoint intervals in the CFT bath, and then apply the quantum extremal surface method, which means include the effect of the dilaton and then do the extremization procedure to find all possible quantum extremal surfaces. So when you have multiple intervals, things start becoming very complicated very quickly. And in fact, you get multiple quantum extremal surfaces and multiple saddles for each quantum extremal surface. And so it becomes very, very quickly very, very complicated. So we do an analysis where we assume, based upon various justifiable arguments, that 2 quantum extremal surfaces suffice. And this is exactly 2 quantum extremal surfaces suffice to describe a single finite interval. But if you have multiple closely separated intervals, they should behave not too differently from a single finite interval. So provided we choose the separations parametrically in the right way, it should be enough to look at multiple intervals and use 2 quantum extremal surfaces to describe the corresponding saddle points for the entanglement entropy. So here's an illustration of the kinds of thing that we're thinking about. So we consider the interval A in the CFT bath, which is now a finite interval, but it could also be a disjoint union of more than one interval. And the quantum extremal surface corresponding to this consists of 2, so there's 2 points or 2 quantum extremal surfaces, and there is a cut which joins these 2. And the causal domain or the causal development associated to this region between these 2 quantum extremal surfaces is exactly what we call the island. Okay, so this is the region which actually supposedly belongs to the Hawking radiation, which is the Hawking radiation, the early Hawking radiation. So what we will assume is basically that 2 quantum extremal surfaces will suffice to describe the entanglement entropy of a finite interval or a certain number of closely separated finite intervals. Okay, so there are further assumptions that we make, again, because we are thinking about the slow evaporation limit where I said times are of order 1 over k. We also, corresponding to that, we also need to take each of the intervals must be of size 1 over k, so they are parametrically large in units of 1 over k. And in general, even with just the assumption of there being 2 quantum extremal surfaces, turns out that when you try to compute the saddle point equations for a general case where you have n intervals, you get order n saddles. And so there's a huge number of potential competing saddles that actually determine the true entropy of the system. So for 2 intervals, which is already very interesting, we find that there are actually 5 viable saddles in general. There are more saddles, but most of them are subdominant, and there are 5 which potentially compete with each other. So we consider the following questions, following physical questions. So we recall the Page curve, which tells us that the early Hawking radiation is correlated with the late Hawking radiation. They're entangled with each other. So if we want to understand how that shakes out in this picture, we consider all the radiation that is gathered at some time t, but which is emitted between the times t equals 0 to times t equal to t page. Okay, so we consider like all the Hawking radiation which is emitted from time t equals 0 to the page time, and then we consider all the radiation, the late radiation, which is emitted from the page time onwards to some late time t. Okay, so we collect these 2 sets of Hawking quanta or Hawking radiations and collect them in 2 spatial intervals at time t in the bath. The 2 spatial intervals, A and B, and we compute the mutual information. So once we have the analytical control, all of these calculations can be done explicitly. We can understand exactly which saddles dominate in precisely this slow evaporation limit. And we find that the mutual information is given by this formula. It's the minimum of this 2 minus 3 times this exponentially decaying bit and 4/3. What this tells us is that the mutual information between the early and late Hawking radiation actually increases with time as from time t equals 0, but eventually at a time slightly greater than the page time, it plateaus. So this tells us that the early and late modes are actually indeed correlated. This is not sufficient to say that these correlations are purely quantum correlations, but we can actually test this by computing things like the conditional entropy, which has to be negative if this correlation is a true quantum correlation, and indeed we can show that this is negative. The conditional entropies are negative, and therefore these correlations that we see between the early and the late Hawking radiations are indeed quantum correlations. So we can do other interesting thought experiments, some of which I mentioned at the beginning of the talk, because we now have a nice evaporating black hole setup where everything can be computed analytically. We can imagine taking a subset. So we can imagine trying to ask what this A equals R, this statement that a late Hawking mode is correlated with an early Hawking mode RB. So if you consider a small subset B of late Hawking modes, which are emitted at some late time between some time t and time t plus delta, where this delta can be very small. So in particular, we can take k delta to be very small. So we basically look at some narrow time interval where we capture some Hawking quanta at late times, and we can ask what is the smallest subset of early modes or early Hawking modes emitted between some time t1 and t2 that maximizes the mutual information between these two. So that would be one way to pinpoint the early Hawking modes, which are maximally correlated with a small subset of late Hawking modes. So this is a calculation that again we can do. We can show that, in fact, the entanglement between this small interval B and an interval of early Hawking modes R is maximized. Its maximum value is just given by 3/2 times the entanglement entropy of this of B, and it tells us that the calculation actually tells us that the past Hawking modes, which are maximally correlated with B, are actually highly delocalized in the early modes. So if you look at the time interval in the past, where you have to search to look at the purifier of the modes B, it's a really large, parametrically large time interval because proportional to 1/k. And we've taken T to be a late time regime, which is past the page time. And so this is in line with the general expectation that the correlation or the entanglement of a late Hawking mode is highly delocalized in early modes. And it's computationally very hard to actually find out which mode, to actually find the late Hawking mode in the early ones. Similar conclusions apply when we search for the maximally correlated modes to the future of B. Again, we find if we ask what is the subset of future mode which is maximally entangled with a small subset of Hawking modes B, we find that that's highly delocalized in the set of Hawking modes in the future. Another interesting experiment we can do is this Hayden-Preskill protocol, which basically tells us that if we throw in a diary, we throw in a small local quench in CFT language at times t equals t0. So this is on top of the shock wave, and you can make the strength of this local quench or the strength of this diary sufficiently small so that you don't have to take its back reaction into account. You can ask, if you throw this diary in at some time t equal to t0, and you want to ask what's the how much Hawking radiation do you have to receive up to some time t to recover this information that's actually thrown into the black hole. So this is a calculation that you can do again, and you can show that by an explicit calculation, you can show that if the diary is thrown in before the page time, you find that this diary is returned a little after page time, and the time after which it is returned is proportional to the S diary, the entropy of the diary that you threw in, divided by the entropy of the black hole times a factor of 1 over k. If the diary is thrown in after the page time, however, it is returned almost immediately. And this is basically mirroring this famous statement which follows from this Hayden-Preskill protocol, that the black hole at late times, an old black hole actually acts like a mirror. If you throw something in, it comes back out almost immediately. So there's all these very interesting thought experiments that we can carry out with this dynamically evolving time-dependent setup. So let me conclude. So what we have seen is that the dynamical entanglement structure of these evaporating black holes within JT gravity is rich and complex. There's, of course, lots of subtle questions about the underlying, the physics of the replica saddles and so on and so forth, which we are putting aside. There's various qualitative expectations that we are seeing by doing these explicit calculations, the detailed calculations looking at the correlations. Various qualitative expectations are actually borne out by explicit computations. There are some technical questions that remain to be studied. For example, do islands with additional quantum extremal surfaces dominate for multi-intervals? That's something that we haven't really looked at. Looking at finite width local quenches, something I discussed at the beginning, where you think of the shock wave as being broad, and what happens when the shock wave is not a delta function and you've got broad distribution of energy being thrown in. And in general, it would be very interesting to understand this shock wave and the ensuing dynamical entanglement structure in the boundary conformal field theory framework, where you think about this whole thing being replaced by conformal field theory coupled to a boundary quantum mechanical system in the way that is natural in a kind of large C CFT description. So thank you very much for your attention. That's all I have to say. Thanks.
Thank you, Prem, for a very interesting talk. We have time for questions. So please unmute yourself and ask him.
Hi, Prem. I have one question. So how should one think of doing these calculations in the presence of replica wormhole picture?
Well, that's an interesting question, because this is a time-dependent setup, and you want to think about the replica wormhole calculation is intrinsically Euclidean, but there is, although I haven't done this calculation, there are actually interesting CFT calculations where you discuss local quenches and computing the entanglement entropy and Renyi entropies in the presence of local quenches, where you implement the replica trick in CFT. And then you can understand how the insertions of the operators in these replicated geometries, how the insertions of these operators move around in the replicated geometries. And you can understand how the exchange of saddle points, okay, how that occurs by actually tracking the locations of these local quench operators in the replicated geometries. You can track them, and you will see that as time goes on, they actually, because you have these branch cuts that are linking different replica sheets, you will find that actually operators in these quench operators, which are inserted from the outside, operators in neighboring sheets start approaching each other. And that's when you expect the exchange of saddles. So it'd be very interesting to see if one can, if there is, I'm pretty sure the same picture works in the dynamical gravity setup where you talk about of the Almeri et al. Papers. But it would be, of course, interesting to see how to make it precise. And
so by some way, does it affect these conical singularities in the replica wormhole picture?
I guess it should, because we should see things evolving as a function of time. Yeah, we should think that these quantum extremal surfaces depend on time. So indeed, yes.
Okay. One more question is that, so how does this shockwave affects the conformal welding problem at the ADS boundary? Does it
this
at all
I don't know.
affect?
It's not something that I've thought about, but it's certainly an interesting question to think about. Yeah.
Thank you. Thank you very much.
Other questions?
Can I ask one more question, maybe?
Yeah, sure.
Yeah. So one last question is that, can I think of lifting this JT story to some higher dimensions, for example, in ATS3? So,
well, yeah, that's the most natural kind of question, and indeed, it's possible that you could try doing something like that if you, because you can think of this whole exercise in the ADS3 language, where you have a holographic dual to CFT with a boundary, and so then you have your bulk. So you have an ADS3 with this so-called end of the world brane, and then you want to understand how putting the shock wave in the CFT or the local quench in the CFT, how it manifests itself in the bulk. In the case where you don't have these end of the world branes, usually inserting this local quench in the CFT corresponds to basically a boosted conical deficit state in ADS3, which is natural because in everything in ADS3 there is no propagating gravity in ADS3. So if you have something energetic that should correspond to a conical deficit state, so an infalling shock wave is like an infalling conical deficit state. So it would be interesting to see if one can actually do the analog of that in the situation where you have ADS3 but with this end of the world brane, and try to ask similar questions. Yeah.
Thank you. Thank you very much.
So I don't see any more questions, and it's getting late here as well. Yeah. So let's thank Prem for a very interesting seminar, and we reconvene again tomorrow at 4:30 p.m. So Arpan or Shubho, is there any other organizational announcements?
So we thanks not as such. We thanks again all the speakers, and 4:30. Also tomorrow there will be again a discuss session at the same time. So it will be great if you can be around.